Mr. Vina here, and again, welcome to Chalk Talk. In today's episode, we will be talking about our sun, our star. Our sun is about 70.6% hydrogen and 27.4% helium. Like other stars, it is a ball of gas. This is our sun. Our sun accounts for 99.86% of the mass in our solar system. It is over a million Earths that could fit inside the sun. And the sun's energy is created by a nuclear fusion. It is traveling at 220 kilometers per second. The sun's hydrogen nuclei are fused together to form heavier and newer element called the helium. This process is called a nuclear fusion. In a nuclear fusion, the temperature must be very hot to allow ions of deuterium and tritium to fuse together. The ions must be sufficient. This will able to achieve the fusion reaction rate, and the ions must be in proximity or close to each other at high temperature to avoid cooling. These are the three conditions of fusion. The hottest layer and its energy is produced from nuclear fusion reactions that is carried outward by photons as thermal radiation. This layer is the core. It is where the energy of the sun is transported primarily or partially by means of convection. This layer is called the convective zone. The light that reaches our planet is the sun's energy that comes from the lowest layer of the sun's atmosphere. This is called the photosphere. The visual surface of the sun that is low density and is relatively transparent. This section resides between the photosphere and beneath the corona. It is also known as the second most outer layer of the sun. This layer is called the chromosphere. Part of the sun that varies in size, shape, and is affected by the sun's magnetic field. It has a temperature of about 2 million kelvins and is exceptionally low in density. This is the outermost region of the sun's atmosphere that is consisting of plasma or hot ionized gas. This is called the corona. The question is, what happens when a star runs out of fuel? A star as big as our sun that has exhausted their nuclear fuel expels most of its material, and only the hot core of the star remains. This will have a mass comparable to the sun, while its volume is comparable to Earth. It will no longer undergo fusion reaction since it has no more source of energy. It will cool down after hundreds of millions of years and will become a black dwarf later. For the meantime, this type of star is called a white dwarf star. A kind of star that begins to fuse helium in the core smoothly and will drain its hydrogen in its core and starts to expand. They are extremely hot and bright. An example to this is Rigel, the brightest star in the constellation of Orion. This star is called a supergiant star. An event that occurs during the last stage of a massive or a supergiant star, resulting in a powerful and bright explosion. This explosion is called a supernova. A massive star, like 1,000 times heavier than our Sun, runs out of fuel, will explode, and becomes a supernova. Sometimes its core collapses and crushed every proton and electron into a neutron. This is a leftover of a supernova activity. Now, composed almost entirely of neutrons, meaning no net electrical charge and slightly massive than protons, they are the densest objects in space. That one teaspoonful would weigh 1 billion tons. They are so compact that they shrink to a size of a city. They can last up to 34 million years. That is why, since they are composed almost entirely of neutron, they are called neutron stars. Once a neutron star mass limit, which is 3 solar masses, is exceeded, the neutron star collapses to a black hole in less than a second. That is how black holes are formed. A region of a black hole where no amount of force can overcome its powerful gravity will be swallowed forever and will vanish, including light, so not even light can escape. This is also called the point of no return. This region is called the event's horizon. And lastly, a place in a black hole where matter is compressed to an infinitely tiny point and where time and space completely break down. This place is called the singularity. The HR diagram is a tool that shows the relationships and differences between stars. The vertical axis represents the star's luminosity or brightness, or sometimes we call them magnitude. The horizontal axis, on the other hand, is the temperature. This enables astronomers to classify stars. This is the Hertzsprung-Russell diagram. The stars in the stable phase of hydrogen burning lie along the main sequence that includes our Sun. Usually their lifespan is about 10 billion years. Red stars are the coolest stars, while yellow stars are hotter than red stars. However, red stars can last up to 100 billion years of lifespan.